working. Let's try. It's a little crooked though. Okay. This is a live stream. Hey, how you doing? Come sign the attendance, Rob. And can everybody hear me? That doesn't look right. Okay. So right over here for me. Yeah. Okay, let's see. I can see, kind of. I know. Okay, let's try this. You can look at the audience right now. Here we go. Yeah, here's our audience members. Everybody here. Okay, live stream. Okay. Let's see. Here we go. Okay, big picture. Okay, it's better. All right, wide angle. Pretty straight. Let's try that again. Okay, there we go. Okay, so hello, hello, hello. Okay, that's working. Okay, so I don't see any. Oh, it's working. Okay. Yay, it's working. Okay, I think we're live streaming. Anybody know how to check? You can go on our website. Should we see if it works? Let's see if it works. Okay. Yeah. Technology. All right, everybody turn to your neighbor and say hello, neighbor. Hello, neighbor. I'm glad you're here. We're going to do better because we're here today. We're going to do better. Say hi to your neighbor. Come on. Say hi. Say hi, neighbor. Okay, let's see if it works. Click this thing. Oh, it's not working. Copy and paste. Good, it works. 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 I got to have fun too, right? All right, so you guys are here for a final exam review. And how many people are in Aaron O'Connor's class? Aaron O'Connor's class. Okay, so I had in mind I would mainly be covering my material, but it's actually your material too. So if at any point you have questions, you wanna break in and ask questions. I give my students a study guide, so that's kind of the guide that I'm trying to follow today. But really, if you have questions at any time, you should stop and ask that question because that's what you're here for, right? You want to understand the material better, okay? So we have a study guide. We have practice questions we can go over. How many people have already done the 10 questions? You did the 10 questions, okay? So those questions are going to be on our final. Actually, Aaron O'Connor has a set of questions too. I don't know if I can show. Oh, I can show them like this, right? Ooh, would you like to see them?
Yes.
Okay. Ooh, I don't know if I'm allowed to do this. It's like photocopying. But if I show them to the screen, then how do you see them? You can't see them. So I have to read them to you. Okay, I have to read them out loud. Okay, so are you guys listening? So you have the following. I wish I had an electronic version. Maybe I do. Hold on 1 second. Let me see if I have that electronic version. And if I do, then I can show you that. So actually, my students should be able to answer these questions too, you guys. So this is very relevant. See, Aaron. Okay, here we go. Aaron, final, helping. All. Okay, I don't have this. All right, too bad. Okay, so that didn't work. So we'll just ask him, I'll ask him out loud for you, okay? So you guys will be able to answer the question, think about it, and then hear the questions, and I'll give you the answers, and then we'll try to see if we can come up. I want to click too, click to see if you get it right. Let's click, right? Why not do that? And click. I'll just make this my class. Doesn't matter. So this way we can see if we're getting the right answers. Okay, so final exam. And here's your study guide. Okay, so we're going to start with Aaron O'Connor's questions for his students. All right, so question number 1, the sun. Okay, this is the question about the sun. A, has a predicted main sequence lifetime of about 10 billion years, and thus will remain about as it is for another 10 billion years. That's question. That's answer A. You're getting ready with your clicker. Okay, in a second, I'm going to tell you the clicker. Okay, actually, you know what? I'll turn on the clicker now. If you'd like an answer, go ahead and click it. Okay. Okay, B has a predicted main sequence lifetime of about 5 billion years, and thus will remain about as it is for another 5 billion years. Okay, choice C has a predicted main sequence lifetime of about 10 billion years, roughly half of which is over. Okay. D will become a main sequence star in about 4.6 billion years. Okay, click an answer. One of those answers. So it's going to live 10 billion years, so it has another 10 billion years. It's going to live 5 billion years, it has another 5. It's going to live 10 billion, but it has half of that done. Or it will become a main sequence star in 4.6 billion years. Okay, everybody click something. See if you got the right answer. All right. Okay, so the sun is a main sequence star right now, so the last answer is definitely wrong. And I hope that you picked C. Okay, oh, you didn't. Okay, it does have a lifetime of 10 billion years, and it has another 5 billion years to go. Okay, it's halfway through its life. So everybody needs to know that. Okay, in this diagram, I'm going to draw a picture. We'll draw a picture. Man, how do I do this? I wish I had his questions. I don't have his questions. Oops, I don't have his. Ooh, that's funny that it does that. Oh, I didn't know it did that. Whoa, that's cool.
John,
yes.
Someone else can log in with their name and their student.
Wait, you mean he showed them?
They don't have it on?
No.
Oh,
No. This is Aaron O'Connor's questions. Okay. All right, so here is a picture of a star. Okay, so I'm going to have to change the camera. So here's a picture of a star. And there is a carbon core. A helium burning shell, and a out here a neutral shell. I don't quite understand this diagram, but whatever. Okay, there's a neutral shell. Okay, that's the diagram. Can you guys see it? That's hard to see. I should have used another color. Can you see it? Roughly? Okay, so here's our picture over here for those of you at home. You can't see that. Okay, here. How about that? Okay, you still can't see. Oh, there it is. Okay, I can see it. So here's the question. In the diagram to the right, which type of main sequence star could never evolve into this right here? Okay, and your choices are O, B, A, and M. All right, so everybody understand which type of main sequence star could never evolve into the picture over there? O, A, O, A, A, oh no, sorry, O, B, sorry, messed up. A, and M. Which type of star could not ever be this picture that I'm showing you right here? Go ahead, what do you think? Which one could never be that? Okay, so core, the ash is carbon, it's burning helium, and has a neutral shell of hydrogen. I should probably say that, but huh? Or a red supergiant. Yeah. Depends, right? Okay, everybody good? You got the answer? Okay, so you said the right answer was M, definitely. Okay, And M, so this is a pretty massive star. Massive stars will be able to fuse heavier and heavier elements and eventually, fuse iron and then die. And what kind of a supernova will that be? A very massive star fuses all the way up to iron and then supernovas, type 2 supernova. Okay, so this is M is the right answer. Okay, so that was the right answer. M. You guys got it? So O, B's, and A's can all do this. Come on in. Everybody good? Okay. All right. So next question. Third question. Third question. The sun will never be a. Okay, you listening? The sun will never be a main sequence star. Is letter A. B. A neutron star is letter B. White dwarf is letter C. Red giant is letter D, or any of these, letter E. Did you hear that? Want me to read them again? Okay, letter A, main sequence star. Letter B, neutron star. Letter C, a white dwarf. Letter D, a red giant. And letter C, any of these. Which one will the sun never be? Okay, he's fond of the never thing. Huh? Maybe that's why they're hard. Exactly. Okay, everybody good? Only 21 of you. Nobody wants to guess. Huh? Come on, guess something. So A, main sequence star. B, neutron star. C, white dwarf. D, red giant. E, none of the above. Okay? And I'm going to click stop. And the right answer was B, neutron star. The sun is a main sequence star. The next stage is a red giant stage. And after the red giant, it will become a white dwarf. Okay? So those are the sun stage. Okay, here we go. Number 4. It is difficult to determine the source of cosmic rays because, okay, here are your choices. It is difficult to detect the source of cosmic rays because, letter A, of their electromagnetic spectrum. What does that even mean? Okay, of their high energy. They are charged particles. They do not travel in straight lines, and they come from so far away. Okay, so one more time. Letter A. It is difficult to determine the source of cosmic rays because A, they have an electromagnetic spectrum. B, they're high energy. C, they are charged particles. D, they do not travel in straight lines. And E, they come from so far away. Which one do you think is the best answer? Oh, I can see. Oops. Okay. You don't know. It's a little tricky. Let me see what he put. I better not tell you the wrong answer. Oh, you didn't put the answer. Uh-oh. I know the right answer. I'm just kidding. Does everybody know what a cosmic ray is? Let's start with that. You know what it is? It's a cosmic ray. It's a charged particle, right, that comes from very far away. Because it's such a high energy, it makes it all the way to the Earth. So what do you think would be the difficulty, right? So you detect it, but it's difficult to see exactly which direction it came from. And if you're off even a little bit with the angle, if you take that back hundreds of millions or billions of light years away, then you can't find where it came from. It's really a difficult job. But the right answer was E. They come from so far away. Okay, it's really difficult to find that. Okay, this is Aaron O'Connor's. This is not my questions. Okay, so a little different style. Okay, a star. This is actually a question that my students you should be able to know the answer to for sure. Okay, a star-like source of highly regular radio beeps. Right, a star-like source with regular radio beeps is a letter A. Oh, let's try it. Oh, stop. Okay, stop. So the right answer was E. How many people got that? Okay, most of you. Okay. This new one, here we go, new one. A star-like source of highly regular radio beeps is A binary star. Anybody like that one? Binary star? Nobody? You shouldn't. Not right. Okay. B, a neutron star. Okay. Okay. I like your question, Aaron. Okay, C, pulsar. radio star. Okay, sorry. D, radio. Video killed the radio star. Okay, and E, a quasar. Okay, so actually, this is confusing. I think he made a mistake by adding neutron star because technically the right answer is what? A pulsar. Okay, which is a rotating neutron star. So yeah, but maybe. But I think the best answer would be pulsar. Okay, I should make sure that that's what he picked. Huh? What's it say? And what is it? A star-like source of highly regular. Yeah, that's a pulsar. That's definitely a pulsar. Okay, everybody pick that? Yes, good for you. Okay. All right. So next one, number 6. When matter, this is something my students should know too, for sure. Okay. When matter is crushed to a point where the electrons are driven into the protons, into the nuclei, leaving only neutrons, which can be compressed no further. The condition is known as, okay, so do you guys know what kind of a situation you're in that you can make this happen? Okay, a star is dying. How big is that star core that's going to collapse and form this weird creature? Does anybody know the answer to that? I think Aaron's class should know this too.
Like a small city.
Like a, okay, sorry, what I mean by is what is the mass, right? What is the mass of this thing that the electrons get forced into the nuclei? It's more than 1.4 solar masses, but less than, who knows the other end? Less than 3. And so what is this thing called where you form a big ball of neutrons? A neutron star, right? A neutron star. So the question is, what keeps the neutrons from pushing into each other? Why doesn't gravity make them collapse as well? So what is the name that we give the force? Are you ready? Is it letter A, electron degeneracy pressure? I'm going to throw the word pressure in. This should be in there. Okay. B, metallic compression. Don't take B. C, neutron degeneracy pressure. D, plasma. And E, supernova. What? Okay, so everybody picked an answer. So the answers were A. So what? Huh?
Open it up.
Huh?
You gotta open up the.
Oh, I didn't open it up. Shoot. Okay, so one more time. A, electron degeneracy pressure. B, metallic compression. C, neutron degeneracy pressure. D, plasma. Or E, supernova. What is the force that keeps the neutrons from going any further? Okay, everybody good? You know this? Okay. I think my students for sure know this. You guys should know this. Everybody should know this, right? So what holds a neutron star up, keeps gravity from collapsing? The answer is, what is it? Neutron degeneracy pressure, C. Okay, neutrons push on neutrons. It's called neutron degeneracy pressure. Okay, if your mass goes above 3, then is it strong enough? It's not strong enough anymore, and gravity will make it collapse. What will you get? A black hole, right? So if you go above 3 solar masses, then you're going to end up collapsing all the way. Okay, 7. We're almost done. 7. If after a supernova, the stellar core retains less than 3 solar masses. Oh, I kind of gave this question wrong. Okay. If after a supernova, the stellar core remains less than 3 solar masses, the result will most likely be a. Okay, oh, sorry, I got to give you the answers. Okay, A, black dwarf. B, black hole. C, neutron star. D, supermassive star. What is that? Don't get tricked. That's nothing. C or E, white dwarf. Okay, so one more time. A, black dwarf. B, black hole. C, neutron star. D, supermassive star. And E, white dwarf. So if the mass is less than 3 solar masses, what are you probably going to get? Okay. So I think you should have said between 1.4 and 3 personally, but that's okay. You guys know what the right answer is. Okay, the right answer is, what was the right answer? It was neutron star, C. Okay, neutron star, C. Okay, so it's not metallic. What was the other one? Oh, not a black hole. No, you have to be more than 3 solar masses to form a black hole. Okay, So you have to keep that straight. It's a little confusing, all these numbers, right? Okay, letter number 8. There's only 9 questions. Oh, I thought there would be 10. Okay. A single teaspoon of a neutron star, if I could show it to you in this room, okay? Everybody understand? A single teaspoon of a neutron star is so dense. Here's the question. A, it would weigh hundreds of pounds. Hundreds of pounds. B, would weigh tens of thousands of pounds. C, would weigh many millions of pounds and probably fall through the earth to the center. Would be weightless is D. And E, would weigh heavily on the mind, body, and soul. That's a joke answer, don't take it, right? Okay, one more time. A single teaspoon of a neutron star, if he could show it to you in this room, would weigh hundreds of pounds, A, tens of thousands of pounds, B, millions of pounds, and probably fall all the way to the center of the earth. D would be weightless. What? Okay, E would weigh heavily on the mind, body, and soul. We're going to take that one. Okay, all right. The right answer was millions of pounds. Millions of pounds. It's incredibly dense. Okay. Last question. Quasars, right? All my students, everybody needs this. Everybody. What's quasar stand for? Who knows what it stands for? Quasi-stellar radio source. Quasi-stellar radio source, right? So it's really bright, very far away, but it doesn't just emit radio, it emits all kinds of light. Okay, okay, what is a quasar? It is a blue and green lasers used in astronomy to point out stars and constellations. B, a type of fruit drink from the health food store. C, quasi-stellar radio sources produced by nearby neutron stars spinning backwards. D, quasi-stellar radio sources produced by supermassive black hole at the centers of galaxies, ripping stars to shreds. E, quasi-stellar radio source, new rock and roll station for real-time streaming on your iPod. Does anyone even have an iPod anymore? Okay, so don't pick E. Okay, everybody got it? So A, blue-green lasers. B, drink. C, okay, so C and D are the only real options, okay? You guys heard that? C, quasi-stellar radio source produced by a nearby neutron star spinning backwards. It's like putting the, right there, man. Okay. And D, new quasi-stellar radio source produced by supermassive black hole ripping a star to shreds. It's at the center of the galaxy. Okay, does everybody know that's the right answer, right? D was the right answer. Okay, D was the right answer. I didn't close it. Okay. All right, so D was the right answer. Okay, so hopefully that helps. Actually, some of those questions are definitely good for my students too. Okay, so without further ado, I'm going to go ahead and start looking at the study guide. Okay, so actually, how do you guys want to do this? Anybody have an idea? I'm just going to go through the study guide, make sure you know everything. But the hardest thing is not necessarily the terms. The harder stuff is down below. So if it gets a little bit too boring just doing vocabulary. Vocabulary needed? Raise your hand. Vocabulary is needed. A little bit? Okay. Okay, so I'm just going to kind of quickly go through right here. Galactic fountain. Anybody remember what that is? Galactic fountain? We got a name. Bob Benjamin was the name. He's a young man. And he discovered streams of matter being sucked into the Milky Way. Very hot streams of matter. And he said, I think it's coming from supernovas that are blasting material. It's leaving the Milky Way, but what force is going to pull it back? The force of gravity is going to pull it back in. And so he created this idea called the galactic fountain. It allows matter to move from one place in the galaxy to another place. That's a pretty cool thing. And Bob Benjamin's paper was reviewed by Lyle Spitzer, right? And he's a pretty famous guy. Okay, Milky Way, what is that? The galaxy, right? Galaxy is one of many billions of galaxies, but for some time we didn't know if the Milky Way was everything. That's in the chapter 16. Caroline and William Herschel, what's important about them? Something special. Who remembers what they did? They did something special. They observed the night sky. What did they do? They counted stars, and they made a map of the stars that they saw, and they found out the Milky Way was a big oval, and they said it's a pancake. It looks like it's on its side though. And where is the sun? In the middle, right? Were they right? No, they were wrong, right? But it was still a pretty cool effort. And then comes along Jacobus Captain. Why is he special? He did the same thing. He counted the stars, individual stars. What was his better technique in measuring the positions of the stars? You remember? He did photographs, right? And he used the negatives to show where the stars were located. What did he find out? It's a big disk, right? And where's the sun? In the middle again, right? Again, he's wrong. So who comes along finally is we have Harlow Shapley. And instead of studying the individual stars, he studied globular clusters. Okay, so vocabulary words. Globular cluster. Who knows what that is? Globular cluster. A bunch of stars in what shape? Like a spherical, yeah, spherical, like a, I don't know, what's this? Like a dandelion or something. So they're spherically arranged. So what force is pulling them together? The force of gravity, but it's acted over a very long time. These are old stars. So because they're so old, they don't have a lot of metals in them. They are first or second generation stars, probably mostly first actually. Harlow Shapley studied the Milky Way's globular clusters. And does anybody remember the number roughly? How many globular clusters are there?
150.
150. That's actually kind of crazy how little there are. And so because of that, he managed to see them. They're not in the disk of the Milky Way. They're found above and below. They're in the halo around the Milky Way. And when he tracked the position of the center of that ball, he found the sun wasn't in the center. And he predicted that, in fact, that was the position of the true center of the Milky Way. He was correct. Okay? So we have parts of the Milky Way that you're supposed to know: the disk, the bulge, the halo, right? Let's bring up a slide just to take a look at that real quick. So in my class, you're supposed to memorize the dimensions of the Milky Way. So what is the width of the Milky Way? The diameter of the Milky Way? Diameter. 15. Sorry, 30 kiloparsecs, right? Radius is 15 kiloparsecs. Where are we at? Okay, so this is a picture. You guys should look at that. This is the slide that shows the disk, the main body. Most of the mass is in the disk, right? Why does it look like this? What principle tells us this is what galaxies should look like if you wait a little while? So a big ball of matter collapses down to a smaller mass, right? It rotates faster. So what is the principle that we talk about? Conservation of angular momentum, right? So things naturally rotate faster, and then they flatten into a disk as a result of what force? What's the major force? What force is organizing galaxies? Gravity. It's all gravity, right? It's all about gravity. You get the main disk. In the middle, you have a bulge, and that bulge is about 1/3 the size of the Milky Way itself. So it's about 10 kiloparsecs across. So speaking of kiloparsecs, what is a kiloparsec? Kiloparsec. 1,000 parsecs. Kilo, right? 1,000. What's a parsec? A little more than 3 light years. 3.26 light years. So 1,000 parsecs would be 3,260 light years. About 3,000 light years. Okay. So how big is the Milky Way? 30 kiloparsecs, or give me in light years. 100,000 light years across. Okay. How big is the central bulge? About 10 kiloparsecs, about 33,000 light years across. Okay. And then we have the halo, right? The halo is where the globular clusters are found, and it's as big as the entire disk, right? So about 30 kiloparsecs or 100,000 light years across. Okay. So the Milky Way has these structures in it. All right. So what did I do? Okay, so the halo. All right, so spiral galaxy. What's a spiral galaxy? It has a central piece and then arms that spiral out of it. How many arms? There's not always the same. Okay, but we have spiral arms. And are the arms light or dark? That's an important idea. Are the arms light or dark? Well, parts of them are light and parts of them are dark. So it's kind of a trick question, right? But what we see, we cannot see the dark parts very well, right? It's a little bit hard to see them. But we see right on the edge of these dark bands of matter, we see stars, new stars forming. Who knows the names of the two kinds of stars, the two classes that we see forming right at the edge? And because of that, we know that they're right on the edge of the cluster, or at the edge of the star forming region. They're called O and B. So if you look right there, O and B associations. So on the edge of the arms, you have brand new O and B class stars. So why don't we just go ahead and review what's special about O and B. So O, B, A, fine, girl, guy, giraffe, right? Kiss me. And then you know that's the order of the what? What is it the order of?
The star classes.
The star, was that?
Classes.
The classifications, but what is that the order of? The underlying, the temperature, right? The temperature of a star. The hottest stars are O, the next hottest are B, third is A, right? And so on and so on. So they're the hottest stars, and because they're so hot, they live their lives very quickly, right? They have more mass, and they live their life much faster. So everything is done faster when you are a bigger mass, right? You get to the main sequence, you live your life, and you leave the main sequence faster, right? Everything is done faster. And how do they finish their life? O and B class stars. They're all going to finish their life in what way? A type 2 supernova. Okay, well, okay. I guess there's still maybe one piece left. It could be a neutron star or a black hole when they're finally finished. Okay. All right. So we got some words. Metallicity. What does metallicity refer to in a star or a galaxy? It turns out. What does it mean? Metallicity. It doesn't just mean metals, right? What does it mean? Not hydrogen and helium. Yeah, anything but hydrogen and helium. Metallicity. So every generation of stars that lives is going to create more heavier and heavier elements. So if you look at the periodic table, there's lots of elements, right? Element number 1 is hydrogen, element 2 is helium, but lots of other elements. Where are the elements created, right? Some of them are created in stars, and then the star blows up and spreads them out into the universe. And after a star blows up, what happens next? The shock wave goes passing through interstellar medium, right? And compresses them and forms little seeds. What happens next? New stars are formed, right? New stars will be born as a result of that star dying, right? The supernova blast causes new stars to form. Do they form by themselves usually? No, they usually form in clusters, groups, right? So you either have two kinds of clusters. What are the clusters? Open cluster. Probably our own sun was born in an open cluster. What's open cluster mean? The stars are going to drift apart. They're not going to stay together. There's not enough gravity. But they're born together. They're born of the same group of material, and they they're made of the same stuff. Okay. So every population, every generation that lives enriches the next generation. So we have population 1 and population 2 stars. That's a generic term that we use. Where do you find the population 1 stars in the Milky Way? And you're supposed to know that those were the first stars that we looked at, which are pretty close to us, in the disk of the Milky Way. So population 1 stars are stars in the disk of the Milky Way. Because they're in the disk, it turns out they're not that old. They're not as old as some of the other stars, and which means they're not the first generation, second, third, probably fourth and fifth, that kind of thing. So they have relatively high metallicity. Okay. The population 2 stars are not in the disk. Where are they found then? In the halo. And they are very low metallicity, even none, actually, in some cases. So they are first generation stars mostly. They have been around as long as the Milky Way has been around. Okay, so we have the word barred spiral. How is that different than a regular spiral? Okay, so I'm going to draw a little quick picture for those people to remind you. I could just bring up a picture, but anyway, you want to just bring up a picture? How did I just do that? I mean, who's better, the Google or me? The Google, right? The Google wins every time. Google, can you find me a picture of a barred spiral? Your wish is my command. You don't get it. You guys live in such a crazy time. You can just ask your computer to show you a picture of something. And it just does it. Like, what? This is like, what? How is that even possible? Okay, that's really good. Oh, look at that beautiful barred spirals. Okay. So the center is elongated and the arms come out of that bar, the ends of the bar. That's called a barred spiral. Is the Milky Way a barred spiral? Yes, it is actually. Yeah, trick question, right? So you need to know that the Milky Way has an extended center. Now in my class, I asked you to know one further thing. What would be a possible mechanism to make a star change from a single center to a stretched out barred center? What would it be? Tidal force is the right answer, tidal force. So what could have a strong enough tidal force? Another galaxy flying past would stretch our galaxy and give it an elongated center. Okay, all right, so that's a lot of vocabulary. Okay, barred spiral. Local group, what's a local group mean? Local group? All the galaxies that are pretty close, right? So can you name a local galaxy besides the Milky Way? Let's try to name a couple galaxies. You should know 3 at least. There's 3 that I think you should know. Okay, Andromeda Galaxy. Everybody know that one? That is the closest galaxy? The closest spiral galaxy. Andromeda Galaxy. How far away is it, just for fun? I think you need to know it, actually. 2.5 million light years away. 2.5 million light years away. And what else do you need to know about the Andromeda Galaxy? It's coming, right? It's on a collision course for the Milky Way, right? You guys learned that? You learned that in class? Yes. Not yet? Oh, shoot. Okay. I don't know if you need to know this then, but I'm going to just tell you it's cool. So how many people know what the future galaxy will be? There won't be 2. The Milky Way and the Andromeda are going to merge, and they will be Milkomeda. That's the name that we've given them. Okay, it's like 8 billion years from now. Don't worry about it. You know, it shouldn't let your day be bad because of that. Okay, now what's the name of let me do 2 other galaxies that are pretty close to us. In fact, the reason I want you to know them is because they're so close. They are orbiting the Milky Way. They're called satellite galaxies. And they're too close. The Milky Way is actually ripping them apart. What are they called? The Large and Small Magellanic Clouds. Those are the 2 galaxies that are right there. And the Milky Way is ripping them apart. The matter is streaming into the Milky Way. We can see it coming in. Right? That's pretty cool. So that's the Large and Small Magellanic Clouds. We didn't, I put Andromeda Galaxy. Oh, they're right here, right? Spiral. Yeah, I know. Okay. So O and V association is the idea that at the edge of the spiral arms, you can find all the new stars. Why aren't there stars in the middle of the spiral arms? Why are they dark? They're dark now, but will they be dark in the future? And the answer is no. In the future, they're going to light up, but they haven't lit up yet. So it takes time for the material to propagate down the arm and start up new stars. And that we call a spiral density wave. Don't worry too much about it. But it goes in a kind of a wave down the arm. So some spiral galaxies have arms that don't have a complete arm. They have little gaps in them. And then others you can see stars all the way along the length. And that's those are both possible. Okay? Sagittarius A should have a star. Anybody know why that's special? Sagittarius A star. What is that? Special, not just a black hole, super massive black hole, 3.1 million solar masses, right? No, 4.1. What am I saying? 4.1 million solar masses. And where is it found? At the center of the Milky Way galaxy, right? So that's our supermassive black hole. Now, can you see a black hole? I know this is actually a previous chapter, but maybe not for you guys. Can you see a black hole? It's black, right? Does it radiate light? No, right? But how do we see it anyways? So this is an important concept. Yes. What's that called? Thank you. It's called, when the black holes feed, when they eat something, you get an accretion disk around the black hole, that glows so hot that it actually radiates what kind of light? Ultraviolet and X-ray light, right? So they're really bright. If you look with the right kind of camera, you can see X-rays coming from all over the place. There's black holes all over the place. Okay, so let's see. Vera Rubin, why is she famous? Something important about her. It's what she did right underneath, right? Rotation curve of what? Of a galaxy, right? She studied the rotation curve of a galaxy. What does the rotation curve of a galaxy look like? You know what, I wonder if I can just do this. I just do this all day long. Rotation curve of galaxy, right? Oh, there it is. I can do this all day long, right? So number one, there's an analogy between a galaxy and a solar system, right? Does it look kind of like a solar system? You've got a bulge in the middle and a disk around it. Doesn't it look like a solar system? Of course it does. So you would understand why when we first began studying galaxies, we thought they would just be like solar systems. Big ones, but like solar systems. So what's special about a solar system? Most of the matter is in the sun, right? As you go further away from the sun, what happens to the strength of the force of gravity? It gets weaker, right? It gets weaker. So the further away you go from the sun, what happens to the speeds of the planets in their orbit? It gets slower. And they have to go slower or else they would fly away from the solar system, right? They would escape. So we would expect that the same kind of thing happens in galaxies, right? What would we expect? The further away from the bulge, the slower the stars travel in their orbit around the center. But it was wrong. So what we expected and what we observed are different, right? We observed that they didn't slow down. In fact, this curve is not the same as in the book. In the book, they even showed that it got a little bit faster. And so this is bizarre. How could it be? We don't understand gravity, right? That's possible. Maybe we just don't understand gravity. Or we can't see all of the matter that is exerting a force. And right now, we've decided to go with that second option. We want to keep gravity. We like it, right? We think it's pretty good. But if we don't, we're getting the wrong answer when we try to calculate the rotation curve, then maybe there is something called dark matter. Okay, so dark matter is invisible matter in a galaxy. What does it do? It exerts a gravitational force and keeps the stars that are out further from flying away. They should fly away. They're going too fast. Okay, so this is a review, but does anybody remember how long it takes the sun to go once around in orbit around the Milky Way? 233 million years. Yeah, that's pretty good. Pretty cool. That might be relevant for your class. Maybe he's talking about that. Every 230 years, 250 million roughly, the sun goes once around the Milky Way. Okay, so we had two possible candidates for this dark matter, which is it's just acting in a gravitational way. The two models are called MACHO and WIMP. MACHO stands for massive, compact, halo object. Massive, compact, halo object. So when you think about things that are really massive but really small, what do you think about? You think about black holes, right? That's what you think about. That is what you think of. That's exactly what I thought about too. And when this theory first came out, I was sure that that was the answer, that there's just black holes everywhere. We can't see them, so we can't see them. But they pull with their gravitational force. Unfortunately, they do have an effect. Every time they fly in front of a galaxy or a star, the light gets concentrated by that black hole, and you get a flash of light. So it should be that if we watch carefully, there will be flashes all over the place every time a black hole flies in front of a star or a galaxy. And so we have predicted how many black holes. It has to be a lot. And it turns out there's not nearly as many flashes, actually hardly any flashes at all. And so the idea is that that's wrong. We would have seen the flashes, we don't, therefore we have ruled it out. So MACHO is not a viable option anymore. We throw that one out. But WIMP is still a possibility. What does WIMP stand for? Yes?
Weakly interacting massive particles.
Okay, so weakly, that's the key word. Weakly interacting massive particle. Massive means what? It exerts a force of gravity, right? Mass exerts a force of gravity. But it doesn't, we can't see it, so it doesn't interact through the electromagnetic force. We can't see it. And we've also determined that it doesn't interact very strongly with the nucleus of atoms, because that would leave another telltale result. It doesn't interact very much at all. So we believe also that it doesn't interact through the strong nuclear force. But there's still the weak nuclear force left behind. Does it interact through the weak nuclear force? We hope so. We don't know yet. But that's the last chance. There's no other forces. Unless there's another force that we discover, but again, that's fine. Maybe gravity is wrong. Maybe we go back to the starting board. Maybe gravity was wrong. That's what will happen. You guys understand that? If there's no WIMPs, then there had to be a new theory of gravity. So something is going to happen. Okay, so here we go. Be able to. And be able to describe Bob Benjamin's interaction with Lyman Spitzer. Lyman Spitzer. So what was it? Lyman Spitzer read, refereed the journal article, and then he actually said that's a really cool idea. It's the galactic fountain idea. So the paper was about the galactic fountain, and he ended up collaborating with Bob Benjamin later on. Okay, number 2, discuss how the model of the Milky Way has changed in the last 250 years. So the first 2 people, the Herschels and Captain, both of them found that the Milky Way was a big disk. But they did it by counting stars, right? Looking at individual stars. And what was their biggest flaw, the biggest problem? They put the sun in the middle. The sun was not in the middle, right? But according to them, it was. Does anybody know why they got the wrong result? What was the big problem with their observation of stars? Can you see all the stars is a clue. No, you can't, right? What stops you from seeing all of the stars? The dust. There's a lot of dust in the way. And so because they couldn't really see all of the stars, they had the wrong answer for the distribution of the stars, okay? So that would be the explanation I would give. So how did the Milky Way center finally get located? Well, Harlow Shapley figured it out by using the globular clusters. They have a center. They're a big spherical structure, and at the center is where we think it is. So where's the center of the Milky Way compared to us? Where are we? Where are we? 8 kiloparsecs, right? So that's a little more than halfway from the center to the edge, right? A little more than halfway. If 15 kiloparsecs is the distance from the center to the edge, and 8 is a little more than half, okay? So actually we're on, who knows where we are? What arm are we on? My class, you should probably know that. I forgot to put it on the study guide notes. Oh, because I put it on earlier? Oh, no.
Memorize.
Memorize? Oh, it is memorized. Oh, it's down here. Okay, good. Okay, we'll come back to that. All right, describe how, what's the difference between population 1 and population 2? Population 1 stars, metallicity or no? Yes or no? Yes. And they are because they're not first generation stars. Where do you find them? Population 1.
Yes.
In the disk, right? They're relatively young stars, they're newer stars. Population 2 stars are found in the halo, and they're young or old? They're old. Metallicity? No, very little or none, no metallicity, okay? Describe the interactions among the galaxies in the local group. So the local group, they're close enough together that gravity is or is not important. Yes, gravity is important. It holds them together. So they're always going to be with us for all eternity, right? Even when the universe gets dark, those galaxies will still be with us, okay? And it gets dark. You guys know that, right? Eventually, it gets cold. We didn't cover that. But if you like that kind of stuff, remember this black holes class? Never mind. Just inserted that 10-second ad. I'm teaching it in the spring, by the way. Okay. All right. So describe the interactions among the galaxies. So there's a couple galaxies that are circling. There's actually probably 3, but 2 of them, the large and small Magellanic Clouds, are orbiting and being ripped apart, and matter is joining the Milky Way, right? We're getting bigger. Our galaxy's getting bigger. Let's see. How do we see the spiral arms? Did we get that? And the collision of Milky Way with Andromeda, we did that already. How do we see the spiral arms? So there's a direct and an indirect method. So direct, we didn't talk about it, right? So we have these cold gases that are dark, there's no stars there yet, that are in the body of the arms. It's the edge of the arms that are lit up with new stars. How do we see the cold, dark material? It's not visible light, but another kind of light. Who can tell me what it is? What type of astronomy let us see directly light coming from actually and absorbed by these dark arms? So radio astronomy. And there's a famous 21 centimeter absorption line that's only possible if the hydrogen in there is very cold. And so that's what we see. We see a hydrogen 21 centimeter line in that region, which is done through microwave and radio astronomy. Okay. All right. And then indirectly, we see the O and B stars on the edge of each arm that are being born and die very quickly. So if we see them, they were born recently. Okay, so they're big stars. Okay, Vera Rubin deduced the existence of dark matter because of the rotation curves of galaxies. They're going too fast. You need to have more matter there. So that's how she found that they exist. So how do machos? I think I did all this already. Okay, did I do this already? Machos and WIMPs will. How will they interact? So through gravity, sure, and hopefully also through the weak nuclear force. Okay. How is galaxy formation similar and different than a solar system? How is it similar? So is the overall structure pretty similar? Central body in the middle, a flat pancake around there. Why is it the same? What principle is the same whether it's a solar system or a galaxy? Conservation of angular momentum, right? We've said it already today. So that's the reason you get pancakes. The force of gravity pulls it down into a nice disk. Okay, but what's different is in a solar system, right? The force of gravity gets weaker the further you get from the center, but that doesn't happen in galaxies. And the reason is that we must have this dark matter there. Okay, it's a little weird for me, by the way. You should tell you that this is weird that I'm telling you about the stuff that we can't see. It disturbs me. It bothers me that there's so much. Does anybody know? Actually, I think it's down here in the memorized, but before I show you, what percentage of the Milky Way is made of dark matter? 90%. Come on, is this a story that I'm telling you? You want to buy a bridge? You know? Really? You're going to buy this? Okay, that is. It's the best we have right now, right? The best theory we have. So, all right. So these are the dimensions. Okay, the Milky Way, the size, 100,000 light years or 30 kiloparsecs. The thickness is about 0.6 kiloparsecs, 2,000 light years. The halo is 30 kiloparsecs. The galactic bulge, 10 kiloparsecs. Oh, there it is here. Okay. The position of the sun is on the Orion Cygnus star. Okay, that's the name that we give it. And the mass, 4.4. I put 4 million. I said 4 million. I said 4.1. I guess it's 4. I don't remember. I would have fixed it. I think it's 4. What do you think? Let's ask the Google. Mass of Sagittarius.
It's about 4 million solar masses.
What is it? 4 million. Okay, 4 million. But that's not what Wikipedia is like. 4.1. Oh, wait a second. No, we don't want to. Okay, here's the deal. There's not a consistent answer.
Yeah,
there's more than one value listed. Okay, so about 4 million. You don't have to worry about it. That's good enough, right? About 4 million. Oh yeah, if you didn't get cookies and candy, did you sign the roster? Everybody sign. If you didn't sign the roster, make sure you do before you leave today. Mine are over here. Aaron O'Connor's are over here. Okay. Percentage of dark matter. Okay, massive. Okay, so I think we're done. Okay, next chapter. Ready to keep going? Now, do you guys want to pause and do the? How many people have already done the questions that I posted? Anybody not do them? Raise your hand. I didn't do them. Okay. It's probably not fair, but you want to look at them?
Yeah.
Without telling the answer?
Sure.
Well, what would be the point, right?
Yeah.
I mean, you get unlimited tries. I don't think you're going to not fail. You're going to get it. Okay, let's just do it. Because this way you guys are in here, you can see my question. Here we go. Final exam. Preview question. Okay, let's see if I get 100%. Okay, I'm gonna do what you guys said. Which of the following, let's see what you got. Which of the four fundamental forces of nature does dark matter experience? Ooh, didn't we just talk about this? What is the right answer? Okay, so go ahead and click. Is it gravity, the strong nuclear force, and the weak nuclear force? Is it gravity and the strong nuclear force, gravity only, or gravity and the weak nuclear force? Think about it as A, B, C, D. Okay? A, B, C, D. What do you think? What is weak? I mean, what is that? What's that?
Smart spark.
It's wrong on the smart word. Don't worry, I'm right. Smart words we know is wrong sometimes. And I even corrected them, but that's not this. Okay, so 30 seconds, good enough. Good chat with your neighbor. You can be like, what do you think? What's the right answer? There's no points here, right? It's just totally just for you. But anyway, okay. So the right answer was gravity and the weak nuclear force, right? Gravity and the weak nuclear force. So if you're in my class, this is actually one of the questions on your final exam. This is a question. You'll look at it and go, oh, I know the answer to that. This is a question on your final exam. I feel like I'm cheating. Okay, all right. Okay, so this is taken from the next chapter, but we'll get over it. The figure below shows what is called the Hubble tuning fork. The Hubble tuning fork. At which labeled point would Hubble have placed an elliptical galaxy? A, B, C, or D? A is in the middle, B is up here, C is here, D is here. Which one did Hubble think was where the elliptical galaxy is located? This is a question on your final exam. So you need to know this for sure, right? And we'll look at it in just a second. But anyways, let's see if you get the right answer. It's either A, B, C, or D, because that's all the answers available. Hubble tuning fork, which one is it? Hubble tuning fork. Okay, so we don't want to waste too much time. But a second, a couple more seconds. Okay, everybody had a chance to guess? Okay, you want to guess? Okay. And the right answer was D. D. Now, oh yeah, D. Most of you got D. Okay. A is not. Actually, A is going to be a spiral galaxy. Okay, so it's going to be D, elliptical. A is spiral. B is going to be an evolved spiral, spiral C. And down there is a C is a barred spiral. Again, evolved barred spiral. We didn't go into all the details. Okay. An astronomer measures galaxy A to have an apparent recessional velocity of 1,000 kilometers. Galaxy B is twice as far away. Because it is twice as far away, right? Galaxy, so it must have a recessional velocity of, and what is the best answer? It's twice as far away, so what is its recessional velocity going to be? It has to be this. Okay, so anybody know what law this is that we're talking about? The Hubble's law, Hubble law, right? The Hubble law says that the recessional velocity, the velocity equals this constant h, the Hubble constant, times the distance, right? So this constant is a number that we now know is 70. That's what it is currently. In my class, you're supposed to know that number. It's 70 kilometers per second per megaparsec. Okay, so there's a question. I didn't put it on the preview questions, but there's a question that requires you to know the current value, just because it's not that hard to remember. Because it's one more than 69. That's why. I'm sorry. I'm being obtuse, but that's what it used to be. Like literally 3 months ago, the right answer was 69, but now it's 70. Okay, there it is. That's what it is. So if you look right here, what happens to this equation? If you multiply the distance by 2, what do you have to do? You have to multiply the other side by 2 to keep it balanced. So if you double the distance, what has to happen to the velocity? It has to double, right? It's a really simple law. But the further away you go, the faster things seem to be going away from us, okay? So the right answer was D. Ooh, most of you got that one. E, yeah, those of you who got E, that's good. That's good. Silly, silly. Okay, review questions. Okay. Roy G. Bibb is the colors of the rainbow. What color is emitted more than any other color from the sun? Right? The center of the sun's spectrum, it turns out, is the right answer. If you can remember that. You know the colors of the rainbow? Roy, you know that thing? Roy, mnemonic, Roy G. Bibb, right? So red, orange, yellow, green, blue. What's the I? Indigo. Yeah, indigo. Not everybody knows that, but you're in science class, and you know that. Okay. So what's the right answer? We got which color is most strongly. So more of this light comes out of the sun than any other color. And we'll stop. The answer was green. That's the right answer. Green. There's more green than anything else, it turns out. Okay, what an exoplanet? What's an exoplanet? You should know what an exoplanet is. Who remembers what an exoplanet is? Yes, we know. What is it? A planet around another star, right? How many stars have exoplanets? All of them. We didn't know that a bunch of years ago, but now we kind of know. And it's not just one, probably many. So if you get lucky, if a planet passes in front of its star, then you can detect that that exoplanet is there. You can measure the little drop in the light, and then it goes back to normal again, right? What is that technique called? What is the technique called? Where you measure the little drop in brightness from the star, and then it comes back again. Okay? If you haven't done it in a while, might be a good thing to review. This question is on your final exam. Let me just remind you, you need to know that for sure. It's on your final. It's a review questions from a previous exam, right? Okay, so 30 seconds, we'll stop. The radial Doppler method. These are, some of these are real and some of them are just distractors. There's no such thing as a fluctuation method. That's garbage, okay? Direct observation. Eclipse method is not the name that we give it. It's kind of like an eclipse method, but it's got another name. Okay? Radial Doppler is real, but of course that one's if the star is coming towards you or away from you, and you measure the frequency shift. But when it passes in front, it's called the transit method. The transit method is the right answer. Oh, most of you got it. That's great. Transit method. Okay. I'm sure Aaron O'Connor's class has to have this too. Which of the following situations has the greatest variation in the tide? The highest high tide and the lowest low tide. This is a review question, right? In what situation do you get the highest high and the lowest low? The biggest variation in the tide. Okay, so you got neap tide. Everybody knows what neap tide is? Neap tide? Neap tides are very strong tides or not very strong tides? No. Very weak tides, right? Weak tide. Third quarter moon, is that associated with a very strong tide or a very weak tide? A very weak tide. Actually, it's called a neap tide. How about that? And how about a first quarter moon? Strong or weak? Also weak, called the neap tide. Whoa, okay. So spring tide, what's spring tide? A very powerful tide, right? Which is associated with which phases of the moon? New and full, right? Every new and every full. And then E, A, B, and C. So you guys picked an answer. The right answer was D. D. Okay. If you got tricked, it turns out all three of those, the first ones are weak. They're really weak type. So the geometry, I love this. I'm just going to keep doing this. Okay. E, I, picture, images, B. Oh yeah, look at that. That's the Google. Show me a picture. Okay. Show me a big picture. Oh, okay. Not quite as big. There we go. So neap tide, the moon is here, up above, and the sun is over here. Which one has a stronger tidal force on the Earth? The moon, right? The moon, because it's so close. Which one has a stronger force of gravity on the Earth? The sun. Okay, that's why the Earth goes around the sun. But the tides are caused by the difference in the force of gravity called the tidal force, right? So just a reminder of that. Okay. All right. Oops. Where'd it go? There we go. Question 7. Ooh, a chart. I think we've seen this before in the last exam in my class. There's a chart with lots of things. Let's look at the columns. Apparent magnitude. What does that mean? Apparent visual magnitude. The brightness as seen from Earth, right? As we look at the sky, how bright is the star up here? What's the next one? Absolute magnitude. What's the difference? You have to move the star. Where they're not going to be different distances, you move them to a distance of 10 parsecs, right? So if they're different brightnesses, why are they different brightnesses? It's not the distance anymore. What would it be? The star's blank. Luminosity. Thank you. That's exactly right. If the luminosity is brighter, what happens to the number? Up or down? It goes down, right? The lower the number. So the negative numbers are really bright or really dim? They're really bright, right? The more negative, the brighter. The distance is measured in parsecs. Thanks for coming. Did you guys sign, by the way? Okay. And then you want some cookies before you leave? Candy. I'm trying to get rid of it. Okay. Parallax. Everybody remember parallax? The further away you go, the parallax angle gets bigger or smaller? Smaller, right? The further away you go. Spectral class, what's that? OBA, fine girl, kiss me, right? Those are the temperatures of the star. Okay, so let's see. That's what it's about. Which of the stars has the greatest surface temperature? Which one's hottest? And so there's a hint. Only the first letter is important, right? For measuring this temperature. Which one has the highest temperature? O would be the right answer, but there's no O class star. So the next one is B. The one that's B is called HR 4621. Okay? That would be the hottest star in that list.
Where's that one?
I have no idea. You want me to tell you? Yeah. But it's not relevant. Right? Oh, I don't know. It's relevant. So I'm getting. You're asking me a question that's not. It's Delta Centauri in the constellation Centaur. How about that? You got me. Okay. What is the subject of the great debate in astronomy? What's the great debate? Great debate was a debate about what the universe is, right? What the universe is. So there were two possibilities. What were the two possibilities? That the Milky Way and everything we see is the whole entire universe. Everything is in the Milky Way. And then there was another one. And so, by the way, what were the funny little shapes that were in the Milky Way? The spiral nebulae, right? The spiral clouds. They couldn't figure out how those form, but they would be inside of the Milky Way. Nobody figured out how they could be formed. Or, alternatively, the Milky Way is one galaxy, and each one of those spiral nebulae is actually another galaxy. So what's the correct answer? The second one, right? We have billions of galaxies. Okay. But what was the nature of the great debate? Which answer do you think works best? Oh, I'll just remind you, this question is on your final exam. I mean, you know that, right? You need to know that. Don't forget this one. Look at this, you're already doing better. Isn't this great? And you gotta get these best. Okay. All right, so let's see if you know the right answer. The answer was the nature of spiral nebulae. Okay, so you got tricked a little bit. Geocentric and heliocentric is where is the sun in the solar system. That's a really tiny picture, right? We have to think big, right? Got to think about galaxy and then the universe big. So it's the nature of the spiral nebulae. The two possibilities were there are gases in the Milky Way or completely separate galaxies, which turns out to be the right answer, right? They are separate galaxies. Okay, a lunar eclipse. By the way, does everybody know that January 16th is a lunar eclipse? It's going to be a good one. You should come on a hike with us, by the way. You're not in astronomy class, but you can still go for a night hike and see the total lunar eclipse. It's gonna be cool. You're gonna really like it. It's not even that late, like 9:30. Like start at 8:30, 8 or so, and then by 10 we'll start coming back. It's gonna be awesome. It'll last like about an hour, and we'll have a picnic and stuff. It's like cool, hanging out with your astronomy friends. Okay, not relevant. Okay, here we go. Observe a lunar eclipse. What phase is the moon for that lunar eclipse? What will the phase have to be? Turns what color? Anybody know? Red, right? The simultaneous sunrise and sunset all around the earth shining on the moon will make it look very dark and red. Right? It'll be beautiful. You will definitely see it because it will be this phase. Gotta be this phase. This is a line, right? The sun, earth, moon, right? It has to be in that order. Okay, so that's a pretty easy question, I hope. The answer was full. 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 Almost everybody got that. Okay, the answer was full. Oh my gosh, this question keeps showing up because enough people keep getting it wrong. This figure shows a binary star system. So you have a smaller star and a larger star. How do I know that star B is a more massive star? Who knows the answer to that? How do I know that star B is more massive than star A? They're orbiting a point called the center of mass, right? So star B goes on a smaller circle and star A goes on a bigger circle. The reason why is star B is closer to the center of mass. The larger mass star is closer to the center. Okay? And so what does it mean? Which one takes more time to go around? That's a trick question. They take the same amount of time. They have to, or else they would stop being across from each other. But they take turns, right? And so what happens is that they both have to be moving at the same amount of time. Do they move the same speed? Who goes faster? Smaller mass star has to go faster because it goes around a bigger circle. Okay? So when the star comes towards you, what do we call that? Go towards your way. It's called the Doppler effect. What is it? Blue shift, right? Thank you. When the star is moving away from you, we see the light shifted towards a lower frequency called the red shift. Okay, so which of the following answers do you like? At the instant shown, which picture is correct? The figure below shows a binary star system. Which of the following correctly characterizes the spectrum of the spectroscopic binary system at the instant shown? So star B is coming towards us or away from us? Towards us, right? And A is going away from us, okay?
You have to open it.
So you got, huh? It's not working?
Yeah.
Oh, it's not open.
Oh, it's not open? Oh, shoot, sorry. Like, why are you answering? What's wrong? That's me. Okay. Sorry. Okay. See the little kicks. Okay, and this question, just by the way, will be on your final exam. All right, anyway. Okay, so 30 seconds. Try to pick it. Okay, so which one? A has a red shift or a blue shift?
Red.
A has a red shift and B has a blue shift. But which one has a greater blue shift? The faster one, right? So that would be A, moving faster has a bigger effect. And so the best answer was star A's spectra is a larger red shift while B has a smaller blue shift. That would be the right answer. Okay, does that make sense? Oh, you got it wrong? Oh, no, you got it right. Most of you got it right. Okay, D was the right answer. Okay, star A has a larger red shift that's moving away. Star B has a smaller blue shift. Okay, here we go. Chapter 16. Lots of terms. Okay, let's see. So we got, keep going. All right, everybody good? Anybody have questions? No? Okay. Keep on moving. Okay. So spiral nebula. What does a spiral nebula look like, right? It's got a center point and arms radiating out of it. There's something called the grand design spiral. What's that? For those of you in my class, you kind of have to know that. It has arms that are well defined. You can see all the way from the center to the edge. You can follow the arms. All of the arms are really sharp and clear. On the other one, flocculent spiral, what happens? There's little gaps, right? So it's kind of like, where's the, so we have a density wave moving down the spiral arm, and it hasn't gotten there yet, okay? So a flocculent spiral seems to be still kind of working on it, right? It doesn't have a nice complete spiral arm. A barred spiral, we already mentioned, has an elongated center. An elliptical galaxy looks like what? Elliptical galaxy, roundish, right? Footballish, right? Could be more stretched out. So it could be spherical or stretched out, right? But it's not flat, right? It's not flat. It's elliptical. Okay, so you don't have to worry about, a regular you have to know about. What's a regular? Not elliptical, not spiral. Why? It's in the process of colliding, right? They're in the process of forming something new. So when Andromeda and Milky Way collide, we're going to see a big mess, which will gradually over time coalesce into a single galaxy. It'll be nice and organized. Lenticular, you don't have to worry about, it's intermediate stage 2. CB, don't worry about that, okay. Those are intermediate stage, don't worry about it. Okay, Hubble tuning fork. What's the Hubble tuning fork? Actually, why don't we ask to Google, show us that picture. Hubble. You can just put these words in. I'm going to show you the picture, right? There's the Hubble tuning fork, okay? So take a look right here. The tuning fork has arms, right? But the main part right here is the elliptical galaxies. So he put a number which showed the evolution of the elliptical galaxy. So the number one thing you want to understand, according to Hubble, what was the youngest galaxy? The elliptical galaxies were the youngest galaxy. And he was thinking about this idea that you and I have already mentioned, right? The idea that at first the cloud is big and maybe spherical, but as it collapses, what will gradually happen? It'll rotate faster and flatten into a pancake, right? So he was saying it hasn't happened yet for the elliptical galaxy. Unfortunately, he was wrong, right? But he thought that they evolved and gradually became the pancake. And so he gave these numbers right here to show that evolution. So more stretched out, elongated, the number got higher. E9 came right before S0. And then the two branches, yeah, questions?
Yeah, so in the straight line, is that called like because it's
Well, does he say that? No, it's not what it's called. It's just they're the elliptical galaxies. But the reason he would have explained that is that they're gradually collapsing and then rotating faster and then forming a disk. So they're getting more and more stretched out. Now, it makes sense, doesn't it? It totally makes sense. Unfortunately, he didn't have complete data. So it was his idea. It was not a bad idea, but we now know that there's something really wrong with that idea. Who can tell me one thing that's wrong with Hubble's way of talking about this? Why is it that elliptical galaxies are not young galaxies? How do we know that for sure? There's no new stars. Who said that? That was good. There's no new stars. If you're a new galaxy, you should have a lot of new stars. You have no new stars in elliptical galaxies. And if you look carefully, you find out there's not a lot of gases that can make new stars there either. In fact, they're mostly full of what is called coronal gases, right? The very high temperature gases, maybe even 10 million Kelvin, very low density gases. So they're not going to ever make stars. So what kind of stars do we see inside of elliptical galaxies? I'm jumping ahead a little bit, but just to remind you, lots of old stars, high or low, sorry, that's not true. Old stars, what color? They have a reddish tinge because they're not young, they're old, right? And then what else? Oh, they have more globular clusters. We'll get back to that in a second. They have more globular clusters. That's another clue. Okay, so megaparsec. You're supposed to know what that is. What's a megaparsec? Million parsecs, right? Mega, million parsecs. That's all, just million. Edwin Hubble. What's special about Edwin Hubble? So what is he special for in this chapter? He settled the great debate, right? He settled the great debate, first of all. Let's make sure we get that part. So what did he find out? How did he settle the great debate? The debate was, what is the nature of the universe, right? Is it just one big thing? Milky Way is everything? Or are those little spiral nebulae actually separate galaxies? And he settled it by looking at which spiral galaxy? Andromeda galaxy. He looked at Andromeda and he found some special stars there. What were they called? Cepheid variables. Okay, so what is a Cepheid variable star? It's a star that gets brighter and dimmer over time, right? And Cepheid variables can be used to determine from the period, you can determine the luminosities, right? The luminosity. So he used Cepheid variables to determine the luminosity and then measure the distance to those stars and found out that they were 1 million light years away. It turns out they were even more, 2.5 million. But the idea is 1 million light years is much, much further than anything else in our galaxy, right? Our galaxy is 100,000 light years across. So to get millions is totally just, it can't be in our galaxy. And so at that point, nobody was debating anymore. It was over. Hubble had settled the debate. Those spiral things are galaxies, and they're not in the Milky Way, right? So that was the settling the debate. Calibration, what does calibration refer to? Anybody remember? Calibrating. Calibration. Got some people. Okay, so we're talking about the cosmic distance ladder. We should use that word first, right? There's a bunch of techniques that we use in astronomy to measure the distance to objects. Starting with the closest thing. What's the closest technique called? And it's called parallax, right? So what's parallax? Hold your thumb out, right? And you wink, one eye then the other. What happens to your thumb? It shifts, right? That's called the parallax shift. What if you hold it really close and do it again? Right? It jumps a lot more. So the appearance that it jumps from one angle to the other is called the parallax shift. So I don't know. Aaron talks about. I'm sure he did. I'm sure he talked about all of it. But let's talk about parallax. Okay, so the idea is. Okay. So the parallax, the idea is you take a picture of a star, and it looks like it's in the stars over here. And then 6 months later, you take another picture, and it seems to have shifted. Okay? So the parallax can only be used if the stars are really close to us, within 1,000 parsecs or so. So only a few stars, a handful of stars really, compared to the stars in the Milky Way can be used with this technique. Okay, so it's the first step on the ladder. And then calibration is the idea that if you want to get the next technique, and the next technique in our ladder is called spectroscopic parallax. Maybe we should just quickly review these. I think Aaron goes into a little more detail. Who's in Aaron's class? Did he talk about that? Does he talk about spectroscopic parallax? He did. Okay, so we should make sure you know this, because he might actually give you a question. I probably am not, but let me just get you ready for him. So let's bring up that slide. All right, so here is our technique slide, right? So there's a bunch of techniques. Together they make a ladder, and the bottom one is called parallax. The next one up is called spectroscopic parallax. And I think if you've watched the video he posted, spectroscopic, it's not really parallax, but it does what parallax does, which is measure the distance to something. But it really uses spectroscopy, right? So it's a spectroscopic parallax because it uses the spectra. So if two stars have the same set of colors coming out of them, the same range of colors, they must be the same temperature. And in fact, you can figure out they must in fact be the same luminosity. They must be basically twin stars. And so you will know that if they have the same spectra, they are two twins of each other. And that means you know their absolute magnitude. If you know luminosity, you know absolute magnitude. If you know absolute magnitude, you know luminosity. These things are basically connected to each other. So the idea is that you can then figure out, if you know its absolute magnitude, the idea is that you compare that to the apparent magnitude, and by seeing that difference, you can figure out the distance to that object. Okay? So spectroscopic parallax just uses that idea that two stars have identical spectra, they are twin stars. Okay? So we call it spectroscopic parallax. So the idea is that the calibration requires that there's a star that you can measure the regular parallax to and also use this technique. There has to be an overlap where you can use both techniques. When you measure that star, you should get the same distance using either technique. That's the calibration step. Okay? So calibration sets the scale for the next technique to be able to say, hey, that's the same distance. That tells me how to get other distances in that technique. And then you jump to the next one up. It's called Cepheid variables. I don't think he's probably going to make you memorize all of this either, but you can see you're just going further and further away. So Cepheid variables, they have luminosity and period, right? All of you guys remember this? The longer the period, the greater the luminosity. The shorter the period, the smaller the luminosity. Above that, we have Tully-Fisher. Not a very cool one, but whatever. There it is. It says that the rotation curves, if you measure them, determine the mass that's in the galaxy and therefore how bright it should be. It's not a very good technique. It's really, really bad. A lot of error. But anyways, it's there and it's pretty good for a range. But it turns out we can use the top two more often than not for things that we need to measure. So the next to the last is called Type 1a supernova. And so if you hear the word standard candle, the Type 1a supernova is one of the best standard candles. What does that mean? Standard candle. It has a known luminosity, a known absolute magnitude. And it has to be the same every single time. What's a Type 1a supernova? Those of you in Aaron's class, I'm not sure when you guys covered this. Did you cover this? Type 1a is a little vague, not so much. Okay, so listen, it's pretty cool. It's a really neat thing. What happened? Who can help them? Well, give me a brief explanation. How do you get a Type 1a supernova? You need to have the right system. What do you need? A white dwarf. You've got to have a white dwarf. And you got to have somebody to steal from, right? A red giant companion usually, okay? And what happens is the white dwarf will steal matter from the companion, and you get a little flash of light called a nova. And this can happen over and over and over again. But every single time, what happens to the white dwarf's mass? It goes up a little tiny bit, a little tiny bit. And you'd be like, oh, it's no big deal. But it is a big deal because there's a limit to how big a white can be, called the Chandrasekhar limit. 1.4 solar masses. And so the day that the red giant gives just a little too much, that star can't be a white dwarf anymore. So how does a white dwarf keep itself from collapsing? Does anybody remember that? What force keeps the white dwarf from collapsing? The electrons, the electron degeneracy pressure. But the day that you get above 1.4, the electrons are not strong enough. And so what happens? The whole thing collapses. And almost simultaneously, all of that matter fuses in one enormous burst of energy called a Type 1a supernova. It's special, right? But we always know that they're going to be 1.4 solar masses. They have very well-defined masses and luminosities as a result of that. So it's a really cool standard candle. Okay? And then finally, our last one, which we mentioned before, it's called Hubble's law. Hubble discovered that other than the local group, every other galaxy is moving away from us. And so he concluded, what did he conclude as a result of that? The universe is expanding, right? The universe is expanding. And that's a big problem, you know, the whole thing. It's like, why, where, you know, but what they started to do though is work backwards. And that led to the concept of the Big Bang. There was a moment when the universe was really small. It's really big now, but it's getting even bigger, right? So the Hubble expansion is showing that the universe is expanding. And the further away you are, the faster things seem to be moving away from us. The universe is expanding. So let's see, is any of this useful? Do you want to look at these pictures? I don't know if any of them are really useful. This is the Cepheid variables, right? The longer the period, the greater the luminosity. So it has a very simple relationship. Holly Fisher, and I've already told you I don't like it. So what it is, very high errors. Okay, but whatever. It says you should know how bright it is by the mass, basically. And you can think about why this is also another problem, right? Are all galaxies the same age? No. So what happens gradually to the light that comes from a galaxy as it ages? Does it get higher or lower? Lower. Eventually it gets very low, right? As the stars die out, then the brightness of the galaxy has to fade, right? This is another reason why this is a difficult technique, right? But if you pick two that are about the same age, maybe, okay, maybe there's times when it works. Type 1a supernova, we just mentioned, is when what becomes a supernova? What is it again? What's the thing that's there just until the moment that it becomes a supernova? A white dwarf, right? A white dwarf which has a companion. It has to be able to grab matter from the companion or it will never go above the limit, right? Okay. And then Hubble. Hubble found that the universe is expanding. And the constant in the book says 69, right? But it's actually 70 now. Okay, the current value is 70. Okay. All right. Okay, let's see. So we covered a lot of this. Oh, okay, here we go. Hubble's law, Hubble constant, right? I think we talked about that already. Active galactic nuclei. Ooh, this is really cool. AGN, right? AGN. So it turns out what we thought was a whole bunch of different kinds of phenomena can now be unified into one model called the active galactic nuclei. So some of the possible names that we heard before were called Seyfert galaxy, type 1 and type 2, and quasars, right? Those were all considered to be incredibly bright objects. And now we know that they're in fact part of the AGN. And so what's an AGN? I bet we can find a nice picture right here. AGN. I'll bet if I just put that up, it'll show up. No? That's funny. Let's see though. Oh, there it is. I knew it. Let's see if we got it. Oh, there we go. Wow. You want black and white? No. Maybe clear. Ooh, that was pretty. But it's black and white. Ooh, okay. Yeah. I don't know. I feel like these are pretty clear. What do you think? Pretty clear? Okay, so what's in the middle of this active galactic nuclei? What's in the middle? SMBH, what's that? Supermassive black hole, right? You need something powerful to make this thing work. And so the power comes from the fact that you have this giant black hole in the middle of it all. And as things come too close, they get ripped apart, and you form this disk around it. What is it called? An accretion disk. Okay. Now, you might see these jets shooting out of it. They're kind of important. And in my class, I tried to emphasize that when you see these jets, they're very interesting. And they're always on the axis, right, of the rotation of this accretion disk, it turns out. What are they indicating? A magnetic field. Thank you. A magnetic field, right? The magnetic field. And so there's a magnetic field because there's an accretion disk. If there's no accretion disk, there's no magnetic field. But with an accretion disk, you get a very powerful magnetic field. The circulation of charged particles in a circle creates a magnetic field. Anybody remember the name for this? It's called the blank, D. Dy. Dyn. Dyna. Dynamo, thank you. Didn't take you long. The dynamo effect says that circulating charges create a magnetic field. Okay. Now, besides the accretion disk, outside of that is a donut of dusty material. So this is an interesting thing. When you look from this side, you actually not only see the super hot accretion disk, but you see this infrared light coming from the dusty part. And that's called the type 2 Seyfert galaxy. If you look from this angle, you just see the accretion disk. That's called the type 1 Seyfert galaxy. And if you look along the axis, you see something called a blazer, which we didn't list, but actually quasars are probably similar. We don't know for sure, but we think that that could be the case. So they emit all kinds of energy along this jet. It's not just particles, it's light as well that gets emitted across that by that jet. Okay, let's call the unified AGN. Unified AGN. Superluminal is a word that means, what's quasar we said? Quasi-stellar radio source, but it turns out they're not just radio now. They emit all different colors of light, X-ray, microwaves, ultraviolet, all these high energy photons. Okay. So I feel like I might have gone over most of this stuff. Describe the nature of the debate. What's the great debate? Shapley, what did Shapley say? Ooh, I think I forgot these guys. I forgot Curtis. Curtis. Shapley, I didn't say that. Okay, all right. Anyway, Shapley was a fan of which side of the debate? Shapley, the guy who did the globular clusters and figured out where the center of the Milky Way was. He thought that everything we see is part of the Milky Way. There's only one big thing called the Milky Way. Curtis, on the other hand, thought that the Milky Way was just one galaxy amongst billions, and he was right. Okay? He recruited. Describe the major differences between a spiral and elliptical galaxy in terms of morphology and the rate of star formation. So what is the shape of an elliptical galaxy? It's kind of rounder, right? It's got either spherical or stretched out oblong, like an egg shape or a football shape a little bit, rounded up. And the more stretched out it is, the more elliptical it has become. And then a spiral galaxy is flat, right? It's like a pancake. So there's really big differences. How about the kinds of stars that you see? In an elliptical galaxy, no new stars, but spirals do. They have new stars. And what color are the new stars that we're going to think about? We're thinking about the brightest young new stars. What color are they? The O and the B stars. They are blue, right? They're blue stars. So spiral galaxies, if you're an astronomer, you describe them as being blue in color. They have a blue color to them. On the other hand, elliptical galaxies are reddish. Okay? So how did Hubble originally interpret the tuning fork? He originally thought, I didn't get to, yeah.
I just want to ask about the,
Which one?
might have forgot.
You forgot the question? Okay, it'll come back to you. Was it on this slide here, maybe?
It was on the question.
Oh,
it's about elliptical galaxies. So, the elliptical galaxies, like, why do they have names called that? Because
okay, so this is a great question. So remember, Hubble thought that the elliptical galaxies were young, like just brand new, and they were starting to collapse. They would eventually flatten out and be pancakes like spiral galaxies are, right? But they don't. It's not right. And the reason is there's no new stars, right? And so what we see is that there's more globular clusters that are going in all random directions. In fact, the stars in general are going in random directions. They're not organized with a single angular momentum direction, right? A spiral galaxy like the Milky Way is really well organized and has a consistent angular momentum. So we think actually it's more likely that two spiral galaxies smashing together forms this kind of messy looking thing that's called an elliptical galaxy. So what's more likely to happen is that you had spiral galaxies, they smash together and cancel each other out. And then you're left with this big blob that looks like an elliptical galaxy. And if one of the spiral galaxies had more energy or more velocity, then the blob might be a little bit longer in that direction, and the other one a little shorter, right? So you can get a different shape elliptical galaxy.
And I also kind of had a question that you said about like it's massive project. So does the white dwarf have to be more massive than the red, like have more mass than the red giants?
No. The white dwarf is just the core left over. And so most of the mass of the red giant stage, this is a great question, right? How does it work, right? So a red giant then becomes a white dwarf if the mass is not too big. Does anybody know the boundary? How much mass can a star have before you can't get a white dwarf at the end? So up to about how many solar masses? The answer is, you know what it is? 8 solar masses. So you start off with 8 solar masses, And you're going to eventually form a white dwarf. But a white dwarf has less than how much? 1.4 solar masses. How do you go from 8 to 1.4? In that red giant stage, you blow away huge amounts of your matter. 80% of your matter gets blown away. And only the core that's left is going to collapse to form the white dwarf. Okay? So does anybody know what happens with the white dwarf though? It's really hot, right? It's white. So what kind of light comes out more than anything else? White dwarf, ultraviolet, actually more ultraviolet. And then all that material that came out of the red giant gets lit up by the ultraviolet photons. What do you get? What's it called? A planetary nebula, right? That's what happens to all those gases. They get lit up after the star collapses and then starts shining. Okay, so that's not 69 anymore. Okay. All right, so describe the major differences. Explain how Hubble, okay, describe the major components. So there's how many components? The supermassive black hole, accretion disk, torus, and I guess the jets, right, would be a feature. So that's it, okay? Those are the features. One more time?
You never explained before.
Which one?
The Hubble interpretation force diagram.
Oh, how the tuning fork? How he was wrong?
Yeah.
He thought that the ellipticals evolved into spirals. But I just mentioned to you that probably it's the opposite. There were spirals first, then they collided and made elliptical galaxies afterwards. Exactly the opposite. And the reason why is because the ellipticals have used up all of their star-forming gases. They don't have them anymore. So spiral galaxies are still forming stars. Elliptical galaxies did that already. And now they're just left with this barren material, right? Okay, so 1/3 of spiral galaxies are barred spirals. That's interesting. That's just kind of a whatever, random fact. The rungs, right? Can you name the rungs in order? So it's the lowest distance ladder rung. What's it called? Parallax. Next one, spectroscopic parallax. Third rung. Hubble used this with Andromeda. Cepheid variable, right? Fourth rung, we don't like it very much. Tully-Fisher, right? Fifth rung, type 1a supernova. Sixth rung, the best one, right? The Hubble law, right? Those are the 6 techniques that we worry about. And the current value is not 69, it is 70, okay? So we have another few minutes. Does anybody have questions or topics that you want to cover? So actually, if you want to look over some of the old, most missed questions, what do you guys want to do? I can jump back. You want to do that? Try that? Okay. You good? Thank you. You want some cookies, Tammy? No. Come on, a handful for later. You're not helping me out. Okay, you want to start with most missed 1? Start at the beginning? Okay. All right, let's see if we can do this together. Should we take a quiz together? We'll take a quiz together. I'm going to tell you guys quiz. Actually, not. All right, here we go. An observer in the northern hemisphere watches the sky for several hours. Due to the motion of Earth, the observer notices that the stars near the north celestial pole appear to move. Ow. Okay, by the way, these are not necessarily the questions that I'm going to pick, but they're not bad. And some of them are good, which is why I made sure to put them on the most missed questions. So maybe some of them, but I wouldn't just study these. If you're one of my students, what do you want to do? Go look at your old exam in the office. You can do that tomorrow. If your exam's not until Thursday, then you also have Wednesday. No, tomorrow, Tuesday, and Wednesday, all 3 days. Okay, somebody is there from 10 to 2, Libby, and if you come after 2, you just knock on my door and I get that for you, okay? And I should be here for quite a while because I'm trying to get all my grading done, and I have a lot to do. So I'll be here probably late. You know, you could come and knock on my door even at 6 o'clock and be like, can I look at my test? I'm like, sure, I'll get your test for you. Yeah.
So what was the time for tomorrow?
What was that? The time? What time? 10 to 2 for Libby, and then after 2, come see me. Yeah, okay. Oh, did you say review? No. The review your exam, right?
Yeah.
Yeah, that's what I'm talking about. Okay. All right, observer watches the sky. How do the stars move around Polaris, the North Star? Yeah. Yes. No. In EBS, there's a number of figures. Yeah, EBS 1. Okay, what do you think? Anybody know? How do the stars move around Polaris when you look at the North Star? Remember how they look? I'll give you a hint, they circle around. And they rise in the east, and they set in the west, and Polaris is over here when we see it. So they go over the top, but they don't stop. Right? They stay up all night. We get lucky. Right? Okay, so what's the right answer? Counterclockwise. Good for you. Did you guys say that? Counterclockwise. Not everybody. Most of you got that wrong. No. Oh, counterclockwise. The answer was C. Question 2. Oh, it worked. It actually worked. Is that right? That was actually pretty very good. Okay. All right. So here's a picture of an atom. There's energy levels in the atom. The lowest energy level is 1. The highest is 4. The figure below shows a model of an atom. Which of the following electron transitions would release a photon with the most energy? Notice that it says release, right? Emit is the right word. It should have said emit, but whatever. Which transition emits the biggest photon? Okay? What do you think? So 1 to 4, you're going to jump from 1 up to 4, 4 to 1, going from 4 down to 1, 1 to 2, or 2 to 1, right? Those are your 4 options. Which one releases the largest photon energy? Okay, release, emit. So the easy way to answer this, if you have trouble with it, is if you're releasing a photon, does the electron gain or lose energy in that? And the answer, it has to lose the energy. It's going to give it up to the photon. So the right answer was 4 to 1. 4 to 1. 4 to 1. Yes, good for you. Oh, this is cool. How old is the Earth compared to the age of the universe? What do you think? How old is the Earth? Anybody know? 4.6 billion years. How old is the universe? 13.6 billion years. Right? That's the right answer, but it's not. So it's close to 5 and close to 15. What's the best answer? 5 is 15. All right, so are you saying 1/3? Yeah, good. Okay, about 1/3 is full. Okay. Oh, I can't see that. Why do stars twinkle? What makes stars twinkle? Twinkling means that the light is, something's happening to the light. You can actually see different colors. So if you look tonight, it's starting to get dark. Over there in the east, the really, really bright star called Capella, if you see it near the horizon, it will turn red and green and orange. You'll see all these colors coming out of it. You'll say, that's a plane. And then you'll be like, no, it's not a plane. It's a star, right? It's twinkling. Why? Same reason, right? What is it? So the real word is not up there, but the word is refraction. Refraction, the bending of light and splitting the light into different colors. Okay. So the right answer was, oh, did I close it? Did I ever open it? I never opened it. Okay, what's the right answer? What's the right answer? Could be a possible question. The right answer is surface variations on the star. No. Interstellar dust? No. Opacity variations. Opacity means opaque, means it blocks the starlight. No. So it has to be atmospheric turbulence, which causes a different refraction. Okay, so that's the right answer. Okay, you guys get it? Yay! Oh, 100%. Which of the following planets can be seen as a crescent phase from Earth? So does anybody know one planet that you can see this with? Any one planet? Galileo saw which planet? You should know that one. Venus, right? Venus is one of the answers, right? Is it the only answer? Is it Mercury, Venus, Mars, or only Mercury and Venus, or all three of them actually, it turns out? What do you think? A crescent, which means a little sliver, right? Which one is it? Crescent. All righty, and the answer was, let's see what you guys picked. Did you pick A and B? No, it was not all three. Oh yeah, it was A and B, that's right. B, that's right. Good. Only the planets that are closer to the sun can have the right geometry. So what is the phase? What does it look like when you look at a planet like Mars, Jupiter, Saturn, Uranus, Neptune? What do you see? Always nearly full, right? Could be like a gibbous, but it's nearly full. Okay, so what time of day? Ooh, anybody remember how to do these questions? What time of day might the moon rise when it is a waning crescent? Waning crescent. Ooh. Anybody have a technique? How do you remember this stuff? You got a technique? Waning crescent. I'll tell you what I do. I think about a waning crescent is between a third quarter moon and a new moon. And so I try to figure out what the right answer is for those, and it must be between those two, right? That's how I do it. So it says rise. Okay, so we got to figure out, for me, I have to figure out when does a third quarter moon rise? Anybody know the answer? At midnight. And when does a new moon rise? At sunrise, like 6 a.m. Okay, so it's between midnight and 6 a.m. What would that be? 3 a.m. is the only answer that makes any sense. Okay, 3 a.m. Did you hear how I did that? That's how I do it. But how do I actually do that? Actually, the way, you got another technique?
You can also subtract, because you can get the time at the highest point.
Yeah.
Subtract 6 hours from it.
Okay, I like that. That's actually what I memorized. Okay, so when is the third quarter moon at its highest point? It's half lit up, right? But the side that's facing the sun is over here for us on the left or towards the east, right? So half of it's lit up at the highest point, right?
Yeah.
So what time is it? Sunrise, 6 a.m., right? It's like 6 a.m. So yes, is that how you did it?
Yeah.
And then it must rise then at midnight. So it rises at midnight. And the new moon, how much is lit up? Nothing is lit up because it's lined up with the sun. The lit up side is facing away from us. Okay, so yeah, you can do it that way. Okay. Okay, let's see. An object moves on a circular path at a constant speed. What is the direction of the force that causes this to happen? And so the question, can you think of an example of an object moving in a circular path at a constant speed? I guess I should stop and reopen, okay. Can you think of an example? Can anybody think of an example? How about the moon going around the earth, right? Or the earth going around the sun, right? That's mine. So you could ask yourself, what force makes the moon go around the earth? Force of gravity. What direction does the force of gravity act on the moon? Towards the earth, which is actually the center of the circle. So we call it, what kind of a force? Centripetal force. It's a center pointing force. Okay, so the right answer was toward the center. You guys get that? Okay, toward the center is the right answer, toward the center. Now familiar? Kind of? Sort of. Oh, here's another one. I think it's so simple. If you are moving in some direction and somebody pushes you in that same direction, do you speed up or slow down? You speed up, right? If you're moving in that direction and somebody pushes back in the opposite direction, what happens? You slow down, right? So it's with you, the force is with you, then you become a Jedi Knight. No, if the force is with you, I slap that in right now. The force is with you, you speed up. Force is against you, you slow down. What happens if the force is to the side? You speed up or slow down? Neither, right? What happens? You just turn, right? All it does is make you turn, change direction, right? So if force is with you or against you, you know what happens, but if it's to the side, all it can do is turn you, right? So when you're on a circle and your velocity is here, the force is perpendicular to you, then it can only change your direction. Okay, blah, blah, blah. All right, so 8. According to, I just give you this? Never mind. I just gave it to you. Okay. According to Newtonian mechanics, an external, there's an extra R in there. Okay, external force acts on a mass with a strength, magnitude, and direction. Which direction will the resulting acceleration be? So if you push, I got to reopen this. Whatever. Doesn't matter. Whatever. What do you think? Opposite, perpendicular, the same, none of the above. So the answer is the same direction as the force, not the opposite. The same direction. Okay. All right. Ooh, I like this question because it's kind of exotic. And I think it's got a bunch of elements in it that you have to understand. So, you know, if I just had to pick a question out of this set, this is probably one of my favorite ones on the set. Seriously, I think it is. Does that mean I'm going to pick it? Not necessarily, but since you guys stayed all the way to the bitter end, let me tell you there's a pretty good chance, right? So if you understand this question, it probably would help. Okay, so it says, what conditions contribute to the long solar eclipse, such as a total solar eclipse of July 11, 1991? So one of the longest on record. Hint, a supermoon means that the moon was at perigee. Do you remember that? So what does it mean if you have a supermoon? Is the moon bigger or smaller?
Bigger.
It's bigger, supermoon, right? So it's at perigee, meaning it's a little closer to the Earth. It looks larger. But what happens during a solar eclipse? What do you see? You see the sun disappear. Where did it go? Behind the moon, right? The moon blocks the sun for just a little bit, okay? So when do you get a long solar eclipse? When the moon is big or the moon is small? The bigger the moon is, the longer it will be. But there's another factor, right? The size of the sun can change. So if you want a long solar eclipse, you want a big sun or a small sun? The smallest sun will be easier to block, and it'll block for a longer amount of time. So what makes the sun change size? And the answer is the Earth going around the sun, right? And sometimes we're a little bit closer, in January actually, we're a little bit closer. That's called perihelion. And then other times we're further away. So the sun gets bigger or smaller. When is the sun smallest? When we're at aphelion, which is in about July or so, somewhere around July. Okay, so what do you think? What's the best answer? How do you get the longest? How do you get the longest solar eclipse? A long one. A lot of words, right? So check with your neighbor, make sure you got the right answer. Let's see if we get the 100%. See if we get 100%. No. Some people pick different answers. Okay, well, anyway. So one's got to be big, one's got to be small. Which one's got to be big? The moon. That would be perigee, right? And which one has to be small? The sun. That would be aphelion. Okay, so the right answer was A. A was the right answer. Okay. A. Galileo. Okay, I guess we should stop them. Okay, want to stop. How about jump past? How about this one? Star A is 4 times. Star A is 4 times. This is a tricky question. So I don't know how much tricky questions I'll put on there, but you know, if you do this one, you can probably do anything simpler, right? So this says star A is 4 times more luminous than star B, but it is also 4 times farther away. So which factor is more important for the brightness of a star? So actually, I'm kind of asking you to remember a formula, even if we don't use it, that the brightness is the luminosity divided by 4 pi d squared. So which factor, L or D, is more important? The distance, right? So luminosity, if it's brighter, should make it brighter, right? If it's a bigger luminosity, it should make it brighter. But if the distance is bigger, what should that make it? Dimmer. And which factor is more important? You multiply this by 4, and you multiply this by 4, but you have to square it. What's the result? Brighter or dimmer? It's going to be dimmer, right? So how much dimmer? So star A is more luminous, 4 times as luminous than star B, but it's also 4 times further away. How bright does it appear? And the answer is, so 4 on the multiplier, but 16 down here, you get 1/4. 1/4 is bright. Or star B, star A is 4 times fainter than star B. That would be the best. Okay, how about this last question? Star A and B have identical luminosities, but star A is twice as far away as star B. How does its brightness compare? Because it's 1 over distance squared, what does it become?
4 times.
Yeah, that's right. So you put in 2, but you square it. What's 2 squared? It's 4. So it's 1/4 the price, right? 1/4 price. Okay, so if you have any questions, want to ask them now? Otherwise, I think we'll stop. Anybody have questions? Questions? You're welcome to ask. You can stay, hang out for a few minutes. Take some candy and cookies. Couldn't you just finish that thing? Anybody want to take the animal crackers so I don't have to look at them anymore? Just take them home and eat them. They're not that many calories. All right, have a good day. Take care. Good luck. That's the end of the stream. Goodbye.
Thanks for taking the time out.
You're welcome. I don't know if that helped or not.